Hi, my name is Sangyeop Lee from Seoul National University. Our paper is about understanding the features in deep reinforcement learning, especially in evolutionary policy optimizations. First, let's take a look into a typical reinforcement learning study process. First, we choose the target environment, such as Atari, Mujoko, etc. Then we suggest our brand new algorithm and train it with the environment. If we have better performance, we are lucky, job's done. But how does it work? Don't know why, it just performs well. We may have the rationale in designing algorithm, but we have a little idea how it actually works. Let's take a look into the advantage actor critic algorithm as an example. In some environments, it performs well, so we are lucky. But in other environments, it does not perform well, so we are not so lucky. We do not have any idea why this result happens. We just report the whole result and say it works better at many environments. How about the evolutionary strategies? The process is not so different. It performs worse in some environments, but performs better in other environments than advantage actor critic. We still do not know why. What's the difference between environments? What's the difference between algorithms? To find out the difference, we need to understand features in those agents. Before we start the content, let's introduce some terminologies. I will call the reinforcement learning as RL, and A2C denotes the advantage actor critic, which is a gradient-based policy optimization algorithm. And ES denotes the evolutionary strategy, which is an evolutionary policy optimization algorithm. Detailed information about these two algorithms are available in the references in the footnote. And I will abbreviate the convolution into conv and convolutional neural network into convnet. There are some obstacles for understanding features in convolution neural network. First, it has too many parameters. They usually have more than hundreds of thousands parameters, sometimes more than millions. And they are also very deep. They have more than 3 layers, usually more than hundreds of layers. It is almost impossible to analyze each layer one by one. Furthermore, it has more interpretability because parameters are just set of real numbers and their meaning is unknown. So, to understand features in convolution neural network, we need some ideas. First, we can visualize the convolution filter rate. The first convolution layer, which is looking at the raw pixel data, usually have interesting pattern. If they have smooth and clear patterns, we can say they are well trained. On the other hand, if they have noisy patterns, we cannot say they are well trained. They may be not trained enough or have low regularization. Another idea is using a technique called image-specific class salience visualization. It uses data gradient, which is gradient of class score with respect to the input image. The data gradient shows the pixels that are sensitive to the class score change. If the class score changes slightly, the values of those pixels change greatly. Then, let us take a look into the features in Deep RL with this idea. Our target environments are Atari 2600 in OpenAI. It has some advantage for our experiments. First, it gives us visual observations, so we use a convolution neural network to model the police network. And it has discrete action space, so we can use class salience visualization. And it also consists of various tasks with various characteristics. We use the convolution neural network with 3 convolution layers and 1 fully connected layer. It has the same architecture as in DeepQ network. We trained it by both A2C and ES. We used advantage actor critic loss for A2C and episodic return fitness for ES. A2C performed better in 4 environments, while ES performed better in the other 4 environments. The score is in the table. We first visualize the convolution filters of the first convolutional layers in both networks. In A2C trained network, filters have smooth and clear patterns, so we can say that they are well trained. But in ES trained network, filters have noisy patterns. So are they not trained enough? Or are they not regularized? Visual inspection only can be misinterpreted depending on the person's perspective. So we tried Kolmogorov-Smirnov test to test whether the weights are random or not. It tests whether the samples are from a normal distribution. If filter weights pass the test, we can say that they are not from a normal distribution, so they are not noise. But if they do not pass the test, we cannot say that they are not from a normal distribution. So we cannot say that they are just a noise or have some signals. In A2C trained networks, some filters pass the test, while in ES trained networks, no filters pass the test at all. So are ES filters totally random? We cannot say that filters that do not pass the test have no meaningful signal at all. Then, how does it work in some environment? We need another analysis to figure out this. So, we apply the data gradient to our network. In a given time step, the data gradient finds the pixels in observation, which are affected the most with the small changes in class score of the action. If a pixel has high magnitude in data gradient, it is important pixel to determine the action. Let us take a look into the class salience. Bright area has higher magnitude in data gradient. For A2C trained network, object pixels in the game have higher magnitude of data gradient, so it seems sensible. But for ES trained network, data gradient seems noisy, so it does not seem well trained. So why is it noisy? It may be because ES is not good at training the space invader environment. So how about environments which ES is good at, such as Centipede? You can see the result in these videos. Data gradient is still noisy in ES trained network. Data gradient of A2C trained networks has more evident patterns. Then how ES work better than A2C in Centipede? Is it just a coincidence? Or are there some signals hidden in noises? So let's remove noise in ES data gradient. Consider that the data gradient can be split into two terms. One is meaningful signal and the other is meaningless noise. The noise must be invariant to the time, but signals changes as the time changes. So difference between signal and noise is the time invariance. So for a given small 5 by 5 patch, we define two concepts. One is episodic salience distribution. It is the distribution of data gradient throughout the episode. It represents the time invariant term or noise of the data gradient. Another concept is frame salience distribution. It is the distribution of data gradient in the given time step. It represents the time-specific term or signal of data gradient. Then we measure the KL divergence between episodic salience and frame salience. If there is small divergence, there seems no signals, but there is large divergence, there seems some signals in the location. So we plotted the KL divergence for each patch in observations. In centipede environment, as you can see, there is a large divergence in right down corner. So there may be some signal in data gradient in the location. Actually, the ES trained agent stays in that location throughout the episode. So the results seem sensible. Then let's take a deeper look into the agent's behavior. A2C trained agent stays vigil and responds more sensitively to the observation. Pixels of game object have large data gradient magnitude, and the agent do more various actions. ES-trained agent, however, use passive tactics with less consideration on the observation. Noise removed data gradient are high in certain location, and it uses small number of action types. Furthermore, it sometimes performs well without observation input at all in some environments. So, how is it possible? Actually, ES-trained agent uses sparse information. In some environments such as Centipede, it is more efficient to stick to a passive tactics than to respond to the observation signal. In Centipede, for example, the task is quite complex, so it is not easy for players to follow reward. However, if the player keep fires bullets in right down corner, they can earn stable rewards without complex action. In these types of environments, ES-trained agents performs better. On the other hand, A2C trained agent uses dense information. In some environments, the agent must respond quickly to the observations, which means dense information. In these types of environments, A2C trained agent performs better. So our conclusion here is that in different tasks, we need different algorithms to obtain different behavior. So there is no free lunch in choosing proper RL algorithm. With these ideas, we are working on the next study. Many tasks in RL have extremely sparse signal. Many gradient-based algorithms find it hard to deal with these environments. It is because they are good at exploitation, but not at exploration. Meanwhile, ES tend to learn sparse information of the task, which means it has good exploration power. So, it is reasonable to try hybrid policy optimization to obtain balance between exploration and exploitation. This hybrid algorithm may deal with various tasks with sparse signal. So this is the end of my presentation. Thank you for listening.